Okay. Yeah, thanks everyone who's still here, I guess, for the last two remote talks. So this talk is about some project that we want to do, and it would be good to get the CoQ community's input on the project. So our motivation is that proof maintenance is challenging, and proofs break a lot over time. They're hard to write in the first place, and when tactics or underlying proof libraries change, then proofs tend to break, and it takes a significant amount of effort to maintain these proofs. And I think this project is mainly trying to investigate how we can automate proof repair. And yeah, so usually people, especially who write ROC or CoQ proofs, tend to write tactical proofs. And tactical proofs tend to be fragile because small changes require major refactoring of the proofs. Like, for example, if one tactic fails or fails to solve what it goals that it solved before, then it's kind of hard to detect where the breakage is, and also kind of hard to fix it. So the goal of this project is to use techniques that have been used in software maintenance to do proof repair, and in particular in program repair. So people in software engineering have faced this quite a lot, and yeah, we're trying to use similar techniques and adapt these techniques to proof repair. And it would be good to get some input on what we're planning to do and if people have advice. So proof maintenance is not something new. So there have been mathematical libraries formalized in Mizar since the 80s, and people have been trying to automatically maintain proofs since the 90s. But even until this day and age, a lot of the responsibility for proof repair falls on the original authors of the proofs. And if these authors are no longer maintaining the proofs or no longer active, then a lot of proofs just become break and become hard to repair over the years. So so automated program repair has seen a lot of success in industry, and they use learning and mining techniques for code maintenance. And there have been some recent developments in proof repair world. So for example, there has been a recent ROC dataset that was published to study proof of evolution. And basically, they have several proofs over several versions of CoQ. And there is some initial work on using large language models to repair proofs as well. So where do challenges lie? So first of all, there are various, again, types of proofs. There are tactical proofs and there are more declarative proofs. And declarative proofs tend to be a bit more robust because they have an explicit structure that aids with the maintenance. And by declarative proofs, I mean like proofs where you declare where you're proving everywhere. So you have a lot of sub-goals or a lot of lemmas with very small proof scripts and so on. Well, one thing that is extremely robust, but kind of painful to write is proof terms. So I have some ROC proofs from back in whenever I learned how to do theorem proving in maybe 2009 that still work on every version of ROC that I've tried them on because they are just proof terms, explicit proof terms. But these were proofs about some logical transformations, and proofs for any sort of verification or verification of programs would be too painful to write this way. So there doesn't seem to be any sort of well-established maintenance strategies or advice about how to even write proofs that are easy to maintain. Maybe there are some, but they're not that widely spread, I guess. And people don't often consider that as a main priority. At least I don't consider that as a main priority when I'm first trying to prove something. So one question also that we have is, how can we identify robust proof patterns? So what we want to do is we want to mine proof repair patterns from data that is collected, and we want to learn some repair templates. So how people repaired previous proofs, and also what sort of proofs broke in the past over time. And maybe that would help us identify what are robust proof patterns that people use. So what we want to do is first data collection, and then mining, and then proof repair. So with data collection, we want to use Coq datasets to identify the historical patterns of breakage and repair. And we want to analyze these patterns. And in terms of mining, we'd have to convert the proof scripts into some sort of abstract syntax tree. This is what people do in program repair world. So they take a program, convert it to an AST, and then they use something called tree differencing to analyze the changes in the program. And we could do the same with proofs because they're programs. But one thing that we get in proof world that people don't have the privilege of in program world is that we could, after we generate the templates and instantiate the templates to get proof repair candidates, we could validate using Coq whether these repairs have actually worked and the new proof actually works. And if the new proof doesn't work, we could iteratively refine our templates until a correct repair happens and our proof is restored. So in terms of data collection, there's a recent data set that we could rely on that contains proof changes across Coq versions. But one thing that we'd like to ask you is whether you are aware of other sources that we should consider. So other big sources of Coq proofs, because there seems to be, like with Isabel, there's the Archive of Formal Proofs. With Coq, I'm not sure. There's MathComp. There's this data set which may or may not contain MathComp. I'm not sure if there are other sources that we should be looking into in terms of data collection. And then we want to analyze the proof evolution and identify failure points and categorize proofs as either fragile or robust. And for the second phase, we want to convert the proofs to some sort of ASTs. Use tree differencing techniques. So these ASTs will not be as detailed as the AST that Coq uses to check the proofs, but it would be sufficient to do tree differencing on it. And we want to extract common repair patterns. Now, for the third phase, we want to generate candidates, validate them using Coq, and iteratively improve our repair. And one practical advantage of that is it would obviously reduce proof engineering, and therefore we're hoping that it would keep more proofs up to date. And in terms of theoretical interest, it would help us also investigate somewhat practical relationship between proof and program repair, or what works and what needs adaptation. And in terms of community benefit, it would be good to learn using existing data what sort of proof styles are robust, and promote modular proof structures and showing how these modular structures result in robust proofs. And it would be great if we could provide a guide on how to write maintainable proofs. And and it would be great if we could have a proof automated repair framework out of this and guidelines for maintainable proofs. And it would be good to get your feedback before we actually go through this and understand what are pain points that you have when you're repairing your proofs by hand. And if you have any advice for us on how we can refine our proposed approach, that would be great. And also data sources. So data sources for CoQ proofs other than the ones we mentioned. Yeah, and if you want to collaborate on the project, we're open for collaborations from this community. So please reach out. It's great to work with others. So yeah, that's mostly it. After we're done with this, we'd like to evaluate it on large proof repos. So yeah, again, if you have other repos than the ones we're considering, please let us know. So yeah, just to conclude, proof maintenance is quite challenging. Software engineering techniques have been quite successful in industry for automated program repair, and they offer promising solutions. It would be good to see how we can adapt these solutions and use them now that we've scaled up verification to enormous libraries and repositories of proofs. And that may help us improve or automate some of our proof repair and keep our libraries up to date. And yeah, finally, we welcome your feedback and collaboration. Thank you for listening. I'm not sure if anyone has questions or comments. I don't currently hear you.
Thank you, Kristen. Any questions from the audience? Yes.
Hello?
Hi. Okay, mic works great. So, Christine, it's Marco Doco. We've met before. I have a silly question that's not immediately answering any of your questions, but it's, you said proof terms are robust. So I was thinking, how bad would it be if you have a developer that dropped out and you have a very proof that's not maintainable anymore? To go back to the version of the prover that where it worked and just get the proof term and remember that, would that kind of make things, well, not maintainable, it's no longer readable, but fine, the proof term stands and is supposed to be robust? Is that a viable approach?
Interesting idea. I'm not sure how, I'm not really a CoQ developer, so I'm not sure how big the proof term would be in CoQ. In Isabelle, for example, that would not be possible because they throw away parts of the proof terms. They're enormous. They can't even store them, so they throw them away once they're checked. I know in CoQ you can theoretically extract a proof term. For a big proof development, it might be gigabytes or terabytes of amounts of term. I haven't tried proof term extraction from in CoQ. Maybe someone in the audience who's a CoQ developer or who has used that feature could tell us if it's viable. But yeah, converting it to a proof term and then trying to reduce the proof term would be one way to try to try to at least do the repair on the proof term or something like that. If the size, yeah. So I guess my answer is I'm not sure. I'm not sure if we'd run into size issues and practicality issues with big developments or not. If not, that would be great. It sounds like a good idea.
It's Enrico speaking. I wanted to answer your question about the size of proof terms. Well, they are big, but not that big. I think that the proof terms for the other theorem were a few megabytes. So it's not, it's viable.
For a big theory file, or?
Yeah, the other theorem was 100 files.
Okay.
I mean, no, the proof terms are not that big, and they are saved on disk. When you compile a CoQ file, you get a VO, and the VO contains.
Yeah.
So they clearly fit your disk. That's not.
So I wonder if the proof term contains just cuts, so whether it contains names to lemmas elsewhere, that also have proof terms, or whether it's like an unfolded everything back to no definitions and lemmas kind of proof term, because then it would be enormous, right?
No, they are not unfolded. You get
So if they're not unfolded, then the problem is not solved, because if any of the underlying lemmas change or the definitions change, then sure, we have a proof term that's linking to something, but that something is something else now. Do you see the... It may solve part of the problem of like tactics changing, but it doesn't change. But the proof will still break. The proof term will still break on the new version if the underlying lemmas and theorems are now different. Does that?
Do you have some idea of the things you expect to break? My experience is for larger developments, the things that break are fairly intricate. So you'll have changes, subtle changes in the way the simplification engines will unfold or not unfold terms. You'll have subtle changes in the way unification works. The more problematic are efficiency breaks. So
Sorry, more
so
problematic
your proof is still valid, but it just doesn't type check.
Oh.
Just takes forever, or just instead of taking 20 seconds, it will take 20 minutes or 20 hours.
Yeah. Okay. So when I say break, I mean actually break. So there's also the proofs that may take way longer, and it would be good to simplify these. But even if we just focus on breakage, I'm not entirely sure, but from experience, it's usually either underlying tactics changing or something getting added, and now things, the tactics behaving. So either tactics behaving differently, or like an underlying lemma being renamed or changed slightly, that would break things that rely on it. So underlying libraries changing. And often when we fix the, like when you do one fix for something, it will work for a lot of other things, because like if you're relying on a lemma in several places and it changes or gets renamed and you fix that, then you can do the fix in various places. So that sort of stuff seems a bit, at least that sort of stuff seems like low-hanging fruit. And I think for us, the idea is, even if you don't get 100% proof, automatic proof repair, this sort of stuff that's time-consuming and not too difficult, maybe for a machine to do, would be nice to fix. And if we get like 80% of the breakages fixed automatically, and you have to do 20% by hand, that would still be good.
I don't think we have time for more questions, but let's thank Kristen again.
Thanks, everyone.
Okay, thank you.